Hello, this is the video abstract of my paper, Computing Isomorphism Numbers of F crystals using the level torsions. Okay, so let's start fixing a base field K, where K is algebraically closed with characteristic P, and take an F crystal over K, M phi. Now, we all know that deuterium modules over K, where deuterium modules are simply F crystals satisfying that phi m is inside Pm, and this category is anti-equivalent to the category of P divisible groups, D over K. So to study these two kinds of objects are essentially the same. You can study one by studying the other one, and vice versa. And a P divisible group D is determined by its finite truncation, dp to the power n for some finite n. Now this finite truncation here is simply the kernel of the map p to the power m from D to itself. And what we mean by determine here is saying that suppose you have another P divisible group E, where the nth truncation of D is isomorphic to the nth truncation of E, then D and E should be isomorphic. Okay, so this is saying that D is not, because it's not an infinite type of object because we know that D is the projective limit of all of these truncations. Like essentially n has to go to infinity, but actually D is determined by some finite truncation. Now notice that this only works when K is algebraically closed. And it is not true if K is not algebraically closed. So therefore it is interesting to study what is the smallest of such n, where is the cutoff is going to be. And this cutoff is going to be called the isomorphism number. And how can we calculate this isomorphism number? By using some basic invariants of D, for example, its codimension and its dimension. There was a lot of conjectures, and especially one by Traverso 30-40 years ago, and he conjectured that the isomorphism number of D should be less than or equal to the minimum among C and D, where C is the codimension and D is the dimension. But in fact, this conjecture only true in certain cases, and it is not true in general. Lau, Nicot, and Varsil recently proved that this n in general should be less than or equal to the floor function of 2 times CD divided by C plus D. Again, C is the codimension and D is the dimension of D. Now they actually also prove that this inequality is optimal in the sense that this inequality can actually be equality for arbitrarily chosen C and D, and they have actually construct such a D so that this is an equality. And the D that they constructed is in the case where D is isoclinic, meaning that D has a unique Newton slope. So motivated by this isomorphism numbers of P divisible group, so how can we carry over this number to the deuterium module and generalize to F crystal? So here we have the definition. So the smallest non-negative number n is called the isomorphism number of the F crystal M phi if for any WK linear automorphisms of M G, such that if G is congruent to 1 modulo P to the power n, then M phi is isomorphic to M comma G phi. Now notice that G phi is still going to be semi-linear, so this is another F crystal. So this is saying that, you know, if M phi, if this phi here is perturbed by some automorphisms which is very close to 1, right, modulo P to the power n, then this the isomorphism type will not be changed. Now, from the definition of the isomorphism number of F crystal, it's not at all obvious that why this number n here has to exist, or in other words, why this n has to be finite. Right? This n could be infinite. But in fact, a non-trivial theorem by Varsil says that this n has to exist for any arbitrary M phi. So the question now is, how do we calculate such n? And In another paper of Xiao, he developed a very technical invariant of the F crystal called the level torsion, which I will not define here, and we will denote it by L. It says that for any F crystal M phi, the isomorphism number has to be less than or equal to the level torsion in general. And in fact, he conjectured that these two things needs to be the same in general. But the case where we have now is that they're equal when M phi is the direct sum of isoclinic F crystal. So this will be a very useful tool for us to calculate the isomorphism number, because if we can get an upper bound of L, then we can get an upper bound of N. And in fact, if we can actually calculate L in some cases, we can get exact value of N. So the main theorem of this paper is the following, saying that if M phi is an isoclinic F crystal, then the isomorphism number has to be less than or equal to the following expression. Is the floor function of the sum of two things, where the first part is E times the summation I greater than lambda, H sub I, and the second summand is the product of lambda and this guy here, which is sigma I less than lambda, Hi, minus sigma I greater than lambda, Hi. Now here I have to explain, lambda is the Newton slope of M phi because it's isoclinic, there's only one. And H sub i's are the Hodge numbers of M phi, and E is the maximum Hodge slope of M phi. So one interesting corollary of the main theorem is that if M phi is isoclinic due to name module, meaning that the maximum Hodge slope is 1, and the number of Hodge slopes greater than lambda should be D, and the number of Hodge slopes that are less than lambda should be C, and this is D, and this is the lambda is going to be D divided by C plus D. So if you plug in all these things here, and you calculate it and simplify it, this N is less than the floor function of 2CD divided by C plus D, which coincide with the result that Lau, Nico, and Xiao obtained in their paper. But I have to mention that this main theorem, or this corollary, does not claim that this is optimal, which is Lau, Nico, and Xiao, they claim in their paper. So this only recovers the upper bound, but it doesn't claim this is optimal indeed. And in fact, this expression here, in general, will not be optimal. It's going to be optimal in this case, but in general, this is not optimal for general F crystals. So I have found one example where I constructed M phi, and then I plug in all these numbers here, but this number is actually going to be strictly greater than the isomorphism number. And another corollary of the main theorem says if M phi is an arbitrary F crystal of rank 2, now here we don't need to have an isoclinic F crystal, then the isomorphism number should be less than or equal to 2 times the smaller Newton slope of M phi. Now notice that here M phi has rank 2, so there are only 2 Newton slope. If you have one less the other one, then you use the smaller one. If they both are equal, then you can choose either one, and this inequality will always hold. And in fact, this inequality are equality in many cases. Thank you for watching.